All right, we're going to start off the Oscillations chapter, which is chapter 15. I'm going to cover the first few sections. All right, so motion which is periodic in time, that is, motion that represents, motion that repeats itself in time. All right, so something like a power line oscillating back and forth when the wind blows past it, earthquake oscillations that move buildings, something like a pendulum that swings back and forth, or something that is attached to a spring that is maybe bouncing up and down, something like a slinky. All right, so these are all forms of oscillatory motion. Now, sometimes the oscillations are so severe that the system exhibiting oscillations actually break apart. So we can look at, there's a famous bridge collapse where the bridge started oscillating back and forth. It hit a resonance frequency, and then it actually ended up collapsing because of the severity of the oscillations. All right, so in the figure, snapshots of a simple oscillatory system are going to be shown. A particle repeatedly moves back and forth about some position x is equal to 0. All right, so going across here, we have our x, and then down we have the time in this graph. So as you can see, the particle starts at 0 and then oscillates to a position of plus xm. So that is going to be the max displacement, or the max x position, right? The furthest out it can go. That's actually also called the amplitude. We'll get back to that in a second. All right, then it's going to oscillate back. Then it's going to increase its speed as it's coming back. Right at this, where it crosses x is equal to 0, it's going to be at its max speed. As you can see, the velocity vector is largest here. Then it starts slowing down again and then stopping at a point. And then it starts speeding up again, and then again has the maximum velocity at x is equal to 0, then starts slowing down again, and then so on and so forth. So if you called this time is equal to 0, so if this position right here is where it started, and it goes through this full oscillation all the way back to its original point, that's going to be called 1 period, and we use capital T for period. All right, so if we start at time t equal to 0, we end at a time that t is equal to the period. Okay. So frequency of oscillation is the number of oscillations that are completed in each second. The symbol that we're going to use for frequency is F, and the SI unit is going to be Hertz, which is abbreviated as Hz. All right, so it follows that since it's the amount of oscillations per second, then that the period is just 1 over the frequency. And vice versa, the frequency is 1 over the period. Because again, the frequency is however many oscillations per amount of time. All right, so if it's 1 oscillation, which is the amount of time that it takes, or the period is the amount of time it takes for 1 oscillation, that's going to give us our frequency. Okay. And also say, again, frequency is the number of oscillations per some amount of time. Okay. So simple harmonic motion. Any motion that repeats itself is periodic or harmonic. If the motion is a sinusoidal function of time, it's called simple harmonic motion, or for short, SHM. Now, mathematically, simple harmonic motion can be expressed as this. So our equation is x of t, and again, this is not multiplying by t. This is basically saying this is x as a function of t, which means there's going to be a t in the function, right? As you can see over here. All right, then it can be equal to xm, which again is the max displacement of the oscillation, times the cosine, and this is where we get that oscillatory equation, times the cosine of omega t plus phi. So omega is going to be our angular frequency. All right, we'll talk about that more in a sec. And then phi is going to be the phase constant or phase angle. All right, so what is all this stuff? So if we were to draw a graph, and this is going to be our, let's say this is our position, x of t, and then this is our time. And let's just say we had a curve like so. All right. So what we have here is a sine curve, and this distance all the way up to the peak, so basically the max displacement, right, which is right there, is going to be our xm. So our amplitude is given by xm. Right, so again, xm is going to be the amplitude, or the maximum displacement of the system. Omega is, again, the angular frequency, and that is 2 pi over the period. So it's basically pi is a displacement, an angular displacement, divided by the amount of time that it takes to go through a full oscillation, right, which is 2 pi. So it's 2 pi divided by the period, or if we want to write this in terms of frequency, it's just 2 pi times the frequency. All right, so the angular frequency, which is omega, is equal to 2 pi times our linear frequency. All right, and then of course t is going to be the time, and time is going to be progressing forward, so at a certain time, the position is going to be changing. And then this phi is going to be our phase constant. So let's say that, so this is a cosine here, but so let's change this into a cosine function real quick, which looks like this. Let's say that we had this cosine function, but it was slightly off phase. So instead of looking like this, it's going to, let me use a different color here. Maybe it looks more like this. Oops. Right? So it's slightly off phase. So really this phi gives us this difference here, the difference between the start of this and the start of our blue curve there. Okay. Okay, so the figure A shows the plots of displacement of two simple harmonic systems that are different in amplitudes but have the same period. All right, so in this case, they have the same period, which means the amount of time it takes for a full oscillation. So again, if we go from here all the way to here, that's going to be one oscillation. Here, all the way to here, one oscillation. So it's taking the same amount of time. However, they have different amplitudes, right? So you see that xm prime is going to be higher up than xm. Now figure B plots the displacement of two simple harmonic systems which are different in periods but have the same amplitude. So in this case, the amplitude is constant, but you have a different period. So if you look at a full oscillation, this is actually going to be two oscillations in the red, as you can see down here. So the period prime is going to be that. Okay, the prime is just this little superscript there. And then one oscillation for the blue, right, in the same amount of time, right? So you have different periods. So the value of the phase constant term phi depends on the value of the displacement and the velocity of the system at time is equal to 0. So if you look at time is equal to 0, you can see, depending on where your function is it in phase, which means that your phase constant is 0, or is it out of phase, which means you're going to have some kind of phase constant. All right, so figure C plots the displacement of two simple harmonic systems having the same period but different phase constants. All right, so you can see, if we're talking about a cosine function, this is going to be exactly on phase because it starts here at 1. However, this max amplitude is slightly displaced, so you're going to have a phase constant, in this case of pi is equal to phi is equal to negative pi over 4. All right. So we can talk about, since we know we can find the position of our object as it's oscillating back and forth, we also want to know what its velocity is and how its velocity is going to change. Well, we know that the velocity as a function of t, again, this is not times t, it's just a function of t, is equal to dx of t dt. All right, we take the derivative of our position function, that gives us our velocity function. All right, so if we take this derivative, this is going to be d dt of our position function, which was given earlier as xm times the cosine of omega t plus phi. So we're just going to take the derivative of that function. What we do is we take the derivative of the function itself and then the derivative of what is inside that function. All right, so our velocity is going to be equal to Right, the derivative of what is inside is just going to be omega, because you're taking this derivative of just this term. The derivative of this term is going to be 0, of course. All right, so this derivative is just going to be omega, because you do t to the first minus 1, which is just t to the 0, which is 1. All right, so you get omega out front, and then, of course, you still have the xm out front. And then you also need to take the derivative of the function itself. So the derivative of a cosine function is negative sine. Right, so we get a negative sign, and then we put in sine, and then what stays inside the parentheses stays the same. So this is just omega t plus phi. All right, so here is our velocity function. Now, the maximum value, or the maximum amplitude of the velocity, is given by this term, which is omega xm. All right, so in the previous case, xm was just our amplitude. Now, omega xm is going to be our amplitude. All right, so the phase shift of the velocity is going to be 1/2, making the cosine into a sine function. Right? If you phase shift it by pi over 2, you basically change the function. And now you can see that here. So our cosine function, which was our displacement function, is now a sine function. And it's actually the opposite of the sine function, because you have a negative sign in there. Right? So you're not going up first, you're going to go down. Okay, so the acceleration can then be given by the derivative of the velocity function. All right, so our acceleration with respect to t is dv of t dt. All right, so it's d dt of our velocity function, which we just found, which was negative omega xm times the sine of omega t plus phi. All right. So our acceleration function is then, of course, all right, so taking, again, the derivative of the inside and the derivative of the function, we do the inside again, we get another omega pulled out, so you end up with a negative omega squared times xm, and then the derivative of a sine function is cosine. So this just ends up being cosine omega t plus phi. All right. Or if you notice, this is our position vector. So acceleration function can also be written as negative omega squared times our position function. Now, the acceleration amplitude is going to be given by omega squared xm, as you can see right here. So this would be the amplitude of the acceleration function. All right, so we can see that in simple harmonic motion, the acceleration is going to be proportional to the displacement, but opposite in sign. So they both have the same function. They're both a cosine function, right? As you can see here, they're both a cosine function. Now, the amplitudes might change, of course, because in this case it's just xm. In this case it's going to be the angular frequency squared times xm. Right, so you're going to have a different amplitude for the acceleration. But the function itself looks the same, except it's inverted. You have this negative sign in front of it, so you get an inverse function. Okay. All right, so now let's look at Newton's second law. Since we could find an acceleration, therefore we know that we can find the force associated with that acceleration. All right, so we're going to start with Newton's second law. F is equal to ma. And the acceleration that we found is going, if we go back to our previous page, remember it's omega squared times x of t. So this is going to be, and there's a negative in there too. So this is going to be, negative m times the mass times omega squared x of t. Right, or I'll just leave it as x, so we don't get confused. All right, so our acceleration really is negative omega squared x. I'll multiply that by the mass. Now, this should look very similar very similar to something we've seen before. This here is a constant, right? The mass is going to be constant. The angular frequency is constant, right? Because it's just 2 pi over the period, and the period's not changing. So if we just call this a constant, this is negative kx, right? We're just saying, well, this is some constant, so we'll just call that k. All right, so what we end up with is f is equal to negative kx. This is Hooke's law, which we saw in a previous chapter when we were talking about springs. Right? Springs have oscillatory motion. Right? They're going to kind of oscillate back and forth. So we would expect to see some sort of connection here with Hooke's law. All right, so that's what we can use to find out the position or the force of a spring. And here we go. Here's our block spring system. Now this is going to be a simple harmonic oscillator. The spring constant of the spring is going to be k, and it's related to the angular frequency omega of the oscillator. All right, so from the previous slide, we showed that k is equal to m omega squared, which is just a constant. So if I wanted to know, for instance, what the angular frequency was, I could just take the square root of k over m, right? Whatever the spring constant is divided by m. That would give me omega. Now we also know that omega is 2 pi over the period. So if I wanted to find the period, I can just replace my omega with 2 pi over the period and then solve for t. And that would get me 2 pi over the square root of the mass divided by k, which is, again, the spring constant. K is equal to the spring constant. All right, and that's going to depend on each individual spring. Basically, how elastic is it? How stretchy is it? All right, so let's go through an example. All right, and this kind of hits on all the different topics that we've talked to so far in this lecture. So a block whose mass m is 680 grams is fastened to a spring whose spring constant, k, is 65 newtons per meter. The block is pulled a distance of 11 centimeters from its equilibrium position at rest, at x is equal to 0 on a frictionless surface, and is released from rest at time is equal to 0. What are the angular frequency, the frequency, and the period of the resulting motion? All right, so that's basically what the situation you have here is. All right, they stretched something out, or they compressed it a distance of xm, which is going to be 11 centimeters, and then they released it. All right. So to find our, let's do our angular frequency first. To find our angular frequency, we're just going to use our equation for angular frequency, which was the spring constant divided by m. That's equal to the square root of 65 newtons per meter divided by our mass, which is 68 kilograms. We need to make sure we convert this value into kilograms. And you end up with 9.78. And since this is an angular frequency, it's measured in radians a second. All right, now we need to find what the frequency is. Well, the frequency has a direct relationship. It's 2 pi over omega. All right, so this is simply going, other way around. So omega over 2 pi. All right, so this is 9.78 radians a second divided by 2 pi radians. All right, so our frequency is 1.57. And this is 1 over seconds would be the units because the radians are going to cancel out. And this is our unit of hertz. All right. And then lastly, they're asking, what is the period? Well, we know the period is simply 1 over the frequency. So period is 1 over the frequency. So this is going to be 1 over 1.56 hertz, which is 0.64 seconds. All right, so this example continues on with a few more parts. The next part is asking, what is the amplitude of this oscillation? Well, there's no friction involved, and the mechanical energy of the spring block system must be conserved, right? So as it's oscillating back and forth, the energy needs to be converted from potential to kinetic, back to potential, so on and so forth. The block is released from rest at 11 centimeters from its equilibrium position with 0 kinetic energy, right? As you release it, it has no kinetic, which means it's all this elastic potential energy from the spring. Thus, the block will have 0 kinetic energy whenever it is again at 11 centimeters from its equilibrium position, which means it will never be further than 11 centimeters from that position. Therefore, its maximum displacement is going to be 11 centimeters. Right? So if I pull something 11 centimeters away from a relaxed spring, that's going to be its max amplitude. It's never going to surpass that. It's never going to gain energy and be able to go past that max amplitude point. All right, so the next question is, what is the maximum speed, which is Vm, of the oscillating block, where is the block when this speed occurs? Okay, so let's look at what the velocity is. Well, earlier we saw that the amplitude of our velocity function was given by omega x of n, right? Basically just the angular frequency times the position, or the max position. Right, so our velocity, max, is going to be equal to omega x max. So it's 9.78, because that's what we found as our angular frequency. And times its max position. All right, so this is going to be 1.1 meters a second. All right, so the last part of the question was, where does this occur? Well, we know that there's zero kinetic energy at the most stretched position, right? Because that's when it's released. It has no kinetic energy right at that point. It's all potential. Then, as it approaches its x is equal to 0 point, so as it's approaching this point here, it's going to be gaining speed and gaining speed and gaining speed. And it's going to reach its max speed right at this point. And then, once it's past the middle point, it's going to start compressing the spring, which is going to cause a force in the opposite direction, which will start slowing it down. All right, so its max velocity is going to be right at the center position here, right? Basically at a position of 0. Okay. Now the next part is, what is the magnitude of the acceleration, of the maximum acceleration? All right, well, we saw that the acceleration amplitude, or the max amplitude, was given by omega squared, xm. All right, this was just that part of the function at the beginning that's outside of the cosine function. So this is going to be 9.78 radians a second, and this is squared, times the max position, which is 0.11 meters. All right, so our max acceleration is then going to be 11 meters per second squared. Oops. All right. Now, where does this occur? If we go back over here, right when it gets to the 0 point, it's changing from a increasing acceleration to a decreasing acceleration, right? Because it's going from speeding up to then slowing down. So its acceleration right around here is actually going to be 0, because again, it's switching from a positive to a negative acceleration. The acceleration then increases and increases as the force increases, the more stretched out or the more compressed the spring gets. So actually, at the max amplitude points over here is when you'll have your max acceleration. Okay. All right, then next part. So they're asking, what is the phase constant phi for the motion? Well, the equation, as I'll remind you guys, x of t is equal to xm times the cosine of omega t plus phi. All right, so they're trying to figure out what this phase constant is over here. Well, we know that at time t is equal to 0, the block is going to be located at this max position. So we can use those as our initial conditions, basically. And that's what they call them here. They call them initial conditions. So we know the conditions of a certain point in time. When t is equal to 0, xm is going to equal to x. Right? It's going to be at its max position. So if we plug those values in, this is just going to be 0.11 meters is equal to 0.11 meters times the cosine of this function. Well, this is at time t is equal to 0. So the first part of this is just going to be 0. So all you're left with is phi. Now, of course, these 0.11 meters are going to cancel out because you have them on both sides. So all you're left with is 1 is equal to the cosine of phi. Now you need to take the inverse cosine to find out what phi is. So take the inverse cosine of both sides. So you have the inverse cosine of 1 is equal to phi. Therefore, phi is equal to 0 radians. Now, it also could be 2 pi radians, 4 pi radians, 6 pi radians, right? Any integer multiple of 2 pi radians could be a solution here, but we're just going to use 0 radians in this case because it's the smallest one. Okay. So the last part is, what is the displacement function x of t for this spring block system? All right, so we know that our displacement function should look like this. That's the cosine of omega t, plus phi. All right, this is what our function should look like. We can go ahead and plug in the values we know. So x of t is going to be equal to our max displacement, which we know is 0.11 meters, times the cosine. Well, we know what our omega is. We found that out in the first part. So our omega is 9.8 radians a second, and then that's going to be multiplied by t, right? And then plus our phase angle, which we found was 0. Okay. Or you could also put in 2 pi or 4 pi, or, but the value would be the same. All right, so simplifying this, x of t is equal to 0.11 meters times the cosine of 9.8 t. All right, and that would be the final equation for this system, right, for the spring block system. Okay, that's it for this lecture. We will pick it up next time.